Welcome to part 2 of forces on inclined planes. If you didn't check out part 1, go back and check that one out first in order for this one to make more sense. So we're going to start again by setting a block on our inclined plane, and then we're going to draw our free body diagram. And we know that there was some gravitational force pulling this object straight down, which we broke up into two components. We said that part of the force of weight, or the gravitational force, would pull this object down the ramp, and part of this gravitational force would hold the object on the ramp. And we called this component mg parallel because it was parallel to the surface and it was the result of the weight. And we called this component mg perpendicular because it's perpendicular to the surface and it is a component of the force weight. Now these are not actually individual forces, they're just how the mg vector, so to speak, splits up the motion of gravity. Now we also said there's going to be a normal force because there's contact between the between the box and the object. And then if this box was being held at rest, which was our example from part 1 that we're continuing here, there will be some friction pointing up against the gravitational portion that's pulling down, and that's static friction that's going to hold this thing at rest. And we established that this had to be the case because if the object wasn't coming up off the ramp and the object wasn't sliding down the ramp, then all these force vectors had to have an alternative to keep it balanced. And so we can see that the mg perpendicular is the same as normal force, and mg parallel is the same as the frictional force. And what we were able to do then was write some net force equations because the object, we know that the object is balanced out. And so we put that the static frictional force was the same as the mg parallel component, and we put that the normal force was the same as the mg perpendicular component. And now what we're going to be doing is taking a look at how to numerically find the perpendicular and parallel components. And that's going to involve just a little bit of trigonometry. Now, in the other videos that we looked at of forces that are acting at angles, what we said was if I had a block or a box and I was pulling this object along a flat surface, but I was pulling at an angle to the flat surface, that we could break up that force into two components, which would describe how much I'm pulling the box over, or we said along the x dimension, and how much I was pulling the box up, which would be along the y dimension. The total force, of course, is the hypotenuse of the right triangle that's formed by splitting up the components, or the force, into components. And so we're going to do something very similar to this. We know that if we have an angle right here that the force is being exerted at, that the opposite and adjacent sides of this triangle are going to be affected by how much the angle is established. And we could use sine, cosine, and tangent to figure those things out. And so we're going to do something very similar here. We can see that the total force, the combined force here, is going to be the hypotenuse of the triangle. So when I go to my free body diagram here of the inclined plane, I know that this force over here has to be the hypotenuse of the triangle because it's the total force. The components make up the legs of the triangle. So if I look at this one, the x component here, or the one that's parallel to the surface, would correspond to this one. And the y component, which is perpendicular to the surface, would correspond to this one. And so what I'm going to do is create a little triangle that uses all those sides. So I'm going to redraw it here just so it's easier to see. So we have our mg vector, which is our hypotenuse. We have our mg perpendicular vector, which is one component. And then we have the parallel component, which I'm just going to reflect down here just so I can make an actual right triangle, but it would be the same as this length. Alright, so here we have a little right triangle. Here's the perpendicular angle, the 90-degree angle, and so now we can start to use some of our trig to solve for each side. Now the angle that the ramp is at, we're going to call theta. Okay, so this is the angle of incline of the ramp. And the angle of incline just tells us how steep the ramp is. Now it would be nice if we could use that angle as our reference for these, because then what we could say is if the angle of your ramp increases, what happens to each of these components? Well, if you think about your logic, right, if you had a steeper incline, the gravitational force would be directed more down the incline than into the incline. If you had a less steep ramp, you wouldn't have as much force of gravity pulling it down, but you'd have more pushing it into the ramp. And so that's the idea that we want to be able to manipulate, right? We want to be able to use this angle, how steep the incline is, to help us know which component gets bigger or smaller. And so that's what we're going to try to use. In order to do that, we're going to find out that this angle up here is actually the same as the angle of the ramp. And at the end of this video, I'll show you a brief proof of why those two angles are equal. I'm leaving it to the end so that if you just want some of the basics here, you can skip that portion. But I encourage you to watch it so that you can expand your understanding. So this angle over here happens to be the same as the angle of the actual incline, which is why we use this angle instead of this angle down here. So now we can use our sine and cosine ratios to help us find out what the sides of the triangle represent. So I'm going to go ahead and start with, I want to find this parallel component that's down here, and I know that that is opposite the angle, and my hypotenuse is right here. So I'm going to write that the sine of that angle theta that I have in my picture is equal to the mg parallel component over the mg total component. So if I solve for mg parallel by multiplying by mg on both sides, I would show that mg parallel is equal to mg times the sine of the angle of the ramp. So this right here would actually give me how much of the force weight is pulling the object down the ramp, or what proportion of the force weight is pulling the object down the ramp. Now we can do something very similar to find the perpendicular component, which is how much of the force of weight is holding the object to the ramp rather than pulling it down the ramp. So this side you can see it's adjacent to the angle that we're using. So I'm going to use cosine. So I'm going to say that the cosine of that angle is equal to the perpendicular component, which is the adjacent side, over the hypotenuse, which is the total force weight. Solving again for mg perpendicular multiplied by mg on both sides. So I have mg perpendicular is equal to mg cosine theta. And there I have both the two components that make up the total force weight. So again, just to reiterate the logic behind this, because after all, physics needs to be logical. And when we look at the parallel component, we can say that this is the part of the weight, the pull of gravity that is directed down the ramp, and this is the part of the force of gravity, or the weight of the object, that's holding the object to the ramp. Now, as the angle gets larger, so as the angle increases, we know that as sine of an angle increases towards 90 degrees, the sine gets bigger and bigger and bigger. When the angle increases, the cosine of the angle gets smaller and smaller and smaller. So whenever sine of an angle gets bigger, the cosine of that angle has to get smaller. And it actually makes sense, because if the ramp got steeper, the parallel component would get bigger, but the perpendicular component would get smaller. Eventually, when the ramp is just straight up and down to where it's not actually a ramp anymore, it's just kind of a board over here, we can see that all of the force weight pulling on this thing is just the parallel component. At that point, at 90 degrees, the sine component is the only component that's really here. There's no component anymore pushing into the ramp. And so we can use these two to help us analyze that. So that's the end of this part. If you want to watch how I figured out that this angle is the same as the angle of the ramp, stay connected. Otherwise, good luck solving problems of forces on inclined planes. Okay, so let's take a look at this. Down here we have theta, which is the angle of our ramp, and we want to show that it's actually the same as that angle over there. So what I've done here is I've drawn a less messy triangle version of our free body diagram, where this purple vector here is the total, the green vector here is the perpendicular component, and the blue one is the parallel component. And so we want to show that these two angles are the same. Now, we've constructed two right triangles. We have this first right triangle over here that is our right triangle that is made up as part of the ramp, and then we have this right triangle over here, which is our force weight right triangle. And what we're going to show is that, according to Euclidean geometry, that all the angles of the triangle should add up to 180 degrees. So we're going to call this angle here theta, we'll call this angle alpha, and then we'll call this angle, the perpendicular angle, let's go ahead and call that one beta. So we know that theta plus alpha plus beta has to all add up to 180 degrees. Now we also know that all angles that lie along a straight line must add up to 180 degrees as well. So this angle over here, which let's call that one gamma, and this angle theta, and this angle alpha. So we're going to go ahead and write that out as well. We have 180 degrees is equal to theta plus alpha, which is that shared angle there, plus gamma. Alright, now if this is true, if they both add up to 180 degrees and they both have the theta and the alpha in them, then the other angle, beta and gamma, have to be the same. But let's just double check to make sure that that is true. Well, if we look at this component, right, which was called the perpendicular component, this one right here, we know we called it perpendicular because it's actually perpendicular to the surface. So this angle gamma over here is really a 90-degree angle. So is this angle beta. Those are both 90 degrees. So now if we say that 180 degrees is equal to the angle theta, which is the angle of the ramp, plus this angle alpha over here, which we also have on this side over here, that angle alpha is the same, and we know that the beta angle is 90 and the gamma angle is 90, right? Then that means that if we have alpha plus 90 and alpha plus 90, the missing angle here, which is the theta, this is the one we're interested in, these two angles have to be equal because they are made up of the same three angles, which should add up to 180 degrees either way. Therefore, we can say that the angle of the ramp is the same as that little angle in the weight triangle over here, because the angles are all congruent to one another. Hope that makes sense. Good luck doing forces on inclines problems.